we have 3 points that we need to cover in this chapter. So again, the first point is a classification of thermodynamic cycles, and we finished this part. Second point is power cycles or heat engines, and we have 2 types of them. We have gas cycles, we have vapor cycles, and now we are talking about the vapor cycles. Third point, we have refrigeration cycles, which is the opposite of power cycles or heat engines. So if you can understand all the concept you are explaining here, so by default you will understand everything like we need to describe in the refrigeration cycles. When we start talking about the power cycles, we start with Carnot cycle. We say this is the ideal cycle. All the steps are reversible. We have 4 reversible steps, 2 isentropic, 2 isothermal, but we have some limitations for this cycle, especially for the turbine and the compressor, because we have 2 phases and there is no turbine, there is no compressor can handle 2 phases. So this is why we have another cycle, which is Rankine cycle. Rankine cycle, this is the ideal real cycle that we have. And again, it has the same components, it has 4 steps, 2 isentropic, 2 isobaric, not isothermal. Instead of isothermal, as we are using in Carnot, we have isobaric steps, as we are doing in Rankine. And we showed how can we calculate the thermal efficiency of Rankine cycle. And last lecture we had an example to solve and to find thermal efficiency of Rankine cycle. Today we will have another example. This one is completing what we said in the previous one. So the previous example said we have a steam power plant operating on the ideal Rankine cycle. We have steam enters the turbine at 3 megapascal at 350 degrees Celsius. So if you have TS diagram, it's important that you know what point represent the inlet to the pump, the inlet to the turbine, the inlet to the compressor, just to put the conditions. This can make solving the problem much easier. So point number 3, this is the point we have here that represent inlet to the turbine. So this point, the temperature at this point is 350. And again, the heat addition in the boiler is isobaric. So the pressure at point number 3, the pressure at point number 2, they have the same pressure, which is 3 megapascal. So this is the pressure at these 2 points. And this one is condensed in the condenser at 10 kilopascal. So the condenser pressure here is 10 kilopascal. So pressure at point number 4, pressure at point number 1, this is 10 kilopascal. We need to calculate thermal efficiency of this process, of this cycle. This is the first requirement. Second requirement, we need to calculate thermal efficiency if the steam is superheated to 600 degrees Celsius. So point number 3 at 350. Instead of 350, we will increase the temperature to 600. So how the thermal efficiency will change? Third requirement, how the thermal efficiency will change if the boiler pressure is raised to 15 megapascal. So if the boiler pressure here, instead of 3 megapascal, we have it 15 megapascal, while the inlet temperature here remains at 600. So here he's just trying to say different scenarios. We explained or we calculated thermal efficiency of this cycle. Okay, if you see the video that we shared with you, so the thermal efficiency for this Rankine cycle was almost 26%. Okay, but here he is trying to have 3 different scenarios and ask you to calculate thermal efficiency for each one of them. This can help you understand how you can increase the efficiency of this Rankine cycle. As we said, the maximum efficiency we can obtain, this is the efficiency we can obtain by Carnot cycle. And again, in the example, in the video, you can see that we calculate the efficiency of Carnot cycle, and it was almost 45%. So we have the maximum efficiency, it's 45%. Based on the conditions of the example in the previous problem, the efficiency was 26%. So we still have plenty, 20% of efficiency that we can try to increase. So the question is how we can increase the efficiency of Rankine cycle. Here he in this example, he's proposing 3 different scenarios. So the first one is the original one we have here. We have this pressure, we have this condition, and then he said we will superheat. Instead of making the outlet temperature from the boiler 350, we will make it 600. Another scenario, he will increase the pressure of the boiler we have here. Instead of 3 megapascal, make it 15 megapascal. Okay. So let's solve the first case we have here. So in the first scenario we have here, again, we will start by whatever information that we know in this one. So based on the given information, the easiest case, we have point number one. Point number one is saturated liquid, and we know the pressure of this point. Saturated liquid, saturated vapor, just one information is enough. Okay, so at point number one, or at state one, we have saturated liquid at 10 kilopascal. Then you can go to the appendix, since this is steam, and you can find enthalpy at this point. So specific enthalpy at point number one, this will be 191.8 kilojoule per kilogram. At this point, find specific volume. Specific volume at point number one, this will be 0.001 meter cube per kilogram. And also find entropy at this point. Entropy at point number one, this will be the entropy of saturated liquid at the condenser pressure. This will be 0.6492 kilojoule per kilogram Kelvin. So now, since we understand the steps, so we know that what are the information we need at this point. We need the enthalpy H1. This is enough, but we need to find H2, H3, H4 in order to find these other enthalpy values. This is why we have the specific volume. This is why also we find enthalpy at this point. Okay. The second point that we have full information about, this is point number 3. It's superheated vapor, but we have two information available. We have temperature given, we have pressure given at this point. So we can go to state number 3. At this point, we have superheated steam. This superheated steam at 3 megapascal, which is 3000 kilopascal, and the temperature 350 degrees Celsius. So again, go to the superheated steam we have, then we find specific enthalpy at state number 3. This one will be 3116.1 kilojoule per kilogram, and also find specific entropy at this point. Why we find specific entropy at this point? Because we know that the path 3,4 is isentropic, so the entropy at point number 3, this is the same as entropy at point number 4. So the entropy at point number 3, this is the same as entropy at point number 4. And this entropy will be 6.745 kilojoule per kilogram Kelvin. So now we have specific enthalpy at point number 1, specific enthalpy at point number 3. So in order to calculate the thermal efficiency, we need to find two information. Specific enthalpy at 2, specific enthalpy at 4. Okay. So how can complete this one? So we can start with analyze the pump. So what if these steps represent the pump? So the pump is it the change we have from 1 to 2, or 2 to 3, 3, 4, 4, 1? Which one represents the pump? 1 to 2, right. So this is the pump, the state, this change from state number 1 to state number 2. If you get back to the previous slide, the slide that we have all the equations, so we can say the work we have, you have to work inside the pump. This one will be enthalpy at point number 2 minus enthalpy at point number 1. This will be the specific volume, P2 minus P1. So what we have in this equation, we have enthalpy at point number 1. We calculated it. It's 191.8 kilojoule per kilogram. We have pressure at point number 1. This will be 10 kilopascal. We have pressure at point number 2. This one is 3 megapascal. And for consistency, make everything in kilopascal, because here we have kilojoule. So this will be 3000 kilopascal. What is the specific volume? It's 0.001 meter cube per kilogram. So we have all the information we need in this example. All the unknowns are here. Just substitute in this equation, and then we can find specific enthalpy at point number 2, the outlet of the pump. This will be 194.83 kilojoule per kilogram. And this is the H2 that we need to find. So here we remain, we need to find the H4, the specific enthalpy at point number 4, and the equation for this. In order to find H4, we have an equation. This equation contains the quality. And why this equation contains the quality? Or the question, do you think all the time we will use this equation? H4 is H1 plus quality of H vapor minus H liquid. So again, why do you think we are using this equation to calculate enthalpy at point number 4? Why we don't directly use the steam table? Exactly, because we have here mixture of liquid and vapor. So again, we are using this one, we are using this quality, which is the fraction of steam we have in a mixture of liquid and vapor, because point number 4, we have it here in the mixture region. If point number 4 is 100% vapor, saturated vapor, superheated vapor, you know the pressure and temperature, go directly to the steam table and don't use this equation. So this is the only case we are using this equation if point number 4 lies in the mixture region. So in this equation here we have H1. We already find it. This is 191.8 kilojoule per kilogram. H of the liquid we have, H of the vapor. So this one, this is enthalpy of saturated liquid at the condenser pressure at 10 kilopascal. This one is enthalpy, specific enthalpy of saturated vapor at 10 kilopascal. So already we have point number 1 is saturated liquid at 10 kilopascal. So HL, this one is H1. So this HL here, this one equal to H1. You can go to the appendix, saturated vapor, 10 kilopascal, find HV, and then subtract both of them. Also in the appendix, you can find this value directly here, HV minus H liquid. And instead of having HV and then subtract, so directly from the appendix, you can find HV minus H liquid. So enthalpy of vapor minus enthalpy of liquid, this is the enthalpy change due to phase change, right? Which is latent heat. Do you remember the difference between sensible and latent heat? So sensible heat, if you are adding heat or removing heat to the system, a result is temperature change. Latent heat, you are adding or removing heat and the result is phase change. No temperature change, no pressure change, and this is what we have here. Here we have this point, we have, this is HV, this point, point number 1, this is HL. So these 2 points at the same horizontal line. Same horizontal lines mean at the same pressure, at the same temperature. So directly you can find this latent heat, the subtraction between these 2 values from the appendix. And this one can be directly 2392.1. So what is missing in this equation? Just to find what is the value of Q, the quality we have. And again, quality have an equation that we can use. So the quality, we can find it from this equation here. This will be the entropy at point number 4 minus specific entropy of liquid divided by specific entropy of vapor minus specific entropy of liquid. So again, specific entropy of point number 4, we find it because it's the same value as the specific entropy at point number 3. So this one is 6.745 kilojoule per kilogram Kelvin. Specific entropy of the liquid, we have it here, which is the specific entropy at point number 1. So we have this value, which is 0.6492 kilojoule per kilogram Kelvin. And again, you can go to the appendix to get this one. This one is specific entropy of saturated vapor at the condenser pressure, which is 10 kilopascal, which at this point we have here, this is specific entropy of the vapor. So this is the point that represents saturated vapor at the condenser pressure. So at this point, we need to find enthalpy, we need to find entropy, or again from the appendix, you can find this delta S directly. SV minus SL at the constant pressure, so from appendix directly we can find this value, specific entropy of vapor minus specific entropy of liquid at 10 kilopascal. This will equal 7.4996 kilojoule per kilogram Kelvin. So we know all the values now that we need to calculate Q, then substitute in the equation, and then this is the value of Q we have. Q will be 0.8128. Take this Q value, substitute in H4, and then you can find that H4, the enthalpy at point number 4, this will be 2136.1 kilojoule per kilogram, and this is the last enthalpy value that we need to calculate. So we know the value of H1, H3, H2, and H4, and this is the 4 enthalpy value we have in this problem. Then what we can do, just use these 4 enthalpy values, substitute in thermal efficiency equation to calculate what will be the value of the thermal efficiency. So in order to have it, we have thermal efficiency. This one is 1 minus Qin over Q out, or net work divided by Qin. Just any one of them. Okay, so we can substitute in this equation by enthalpy value. So the amount of heat added in the boiler, can anyone tell me the amount of heat added to the boiler? Which enthalpy minus which enthalpy? What is the step representing the boiler? 2, 3. So the Qin will be enthalpy at point number 3 minus enthalpy at point number 2. So Qin, this one will be 2921.3 kilojoule per kilogram. Also Q out, we have here, anyone knows what will be the value of Q out? H, what are the two H value you will use to calculate Q out? Where is Q out happening? 4 minus 1. Q out happening in the condenser, and the condenser is represented by this process. This is the process that represents the condenser. So Q out, this will be H4 minus H1. So this will be 1944.3 kilojoule per kilogram. Substitute in the equation, then we can say thermal efficiency we have. This will be 0.334, which is 33.4%. So this means when we solved the same example, in the previous lecture, we had the efficiency was 25%. Now we start to make some changes in the same Rankine cycle, and we successfully increased the efficiency we have. In the same problem, we have requirement B, requirement C, all of them different scenarios. If you repeat the same calculations, the same steps for requirement B, requirement C, you will see that the thermal efficiency is more than 26%.